center. And what you can see also, if you analyze data inside our galaxy, we also see the need for a very abundant component that we don't see. And just as a final reference, this little pocket in your genes, which nobody knows what it is there for, is to carry 10 GeV of dark matter at all times. So now you know. From the theoretical point of view, going to theories beyond the standard model is probably a theorist's dream. We have come up with very different ways in which dark matter could have been formed in the early universe and in which it could make up this 26% of the energy density. In this plot, very schematically, I'm representing the typical interaction scale as a function of the mass of the different dark matter candidates that have been proposed. And the first thing you would notice is that there is about 50 orders of magnitude on the vertical axis and about, well, essentially the same 50, 60 orders of magnitude in the mass dimension. Dark matter candidates are so diverse that there's not a single way to look for all of them. So actually efforts have to be put into looking for specific candidates one at a time and trying to come up with complementary search strategies. Here, for example, you've got the very popular weakly interactive massive particles. These are particles which interact through an interaction scale of the same order of the electroweak interaction. The motivation for these particles is that they could have been formed thermally in the early universe in the right amount. But there are some other particles which have a completely different cosmological history. And this is actually something very, very interesting, which is by finding the dark matter and by identifying it, we may end up knowing what the cosmological history of the universe was. Okay, so dark matter is also a window to what were the first seconds, if you want, or fractions of a second in our universe. So again, when you look at this plot from the point of view of a theorist, you're very happy because you say, wow, I have so many different ways of producing dark matter. And if you're an experimentalist, you go, oh no, not another model. How am I going to test that? Okay, well, I mean, this is not really true. Experimentalists are also very happy people, right? Dark matter can be searched for in different ways. And again, the goal is to cover that wide parameter space in complementary ways. We can look for dark matter dispersion on terrestrial experiments, underground experiments, and this is what we call direct detection. This is the type of search I'm going to concentrate on today. But we can also look for dark matter in accelerators, for example, producing it at the LHC. Through the collisions of protons, the dark matter particle would be just a stable particle that escapes the experiment, leaving, for example, some missing transfer momentum or transfer energy. There are as well astrophysical and cosmological probes of dark matter. Dark matter can be produced in the inside of different astrophysical bodies. And then we have different implications. For example, it can lead to overcooling of supernovae or other stars. And this is also related to indirect searches. We can look for the products of annihilation or decay of dark matter in those places in the universe where it is abundant, for example, in the galactic center. Finally, in the last few years, probably a new window to look for dark matter has opened, which is gravitational waves. The presence of dark matter along the way of gravitational waves can also induce some modifications in this that can also be observed. So as you see, we have a rich way of looking for dark matter particles. Spoiler alert, we don't have yet any confirmation of dark matter having any interaction which is not gravitational. So like I said, I'm going to concentrate on direct detection. And the canonical signature there is to have a dark matter particle approaching at non-relativistic speeds. The dark matter velocity, typical velocity in our dark matter halo at our position in the galaxy is about 200, 300 kilometers per second. This dark matter particle collides with the nucleus, and being invisible and stable, it just disappears, leaving us only a recoil energy which is of the order of the kilo-electron volt. The way to look for this experimentally, depending on your experimental target and device, this can lead to ionization, scintillation, an increase of temperature. There are different ways in which this recoil energy can be transformed. Because of the energy range of the recoil spectrum, typically these type of searches are sensitive to masses above 1 GeV. However, in the last decades, we've also realized that direct detection experiments can also be sensitive to dark matter particles interacting with electrons. And this is very interesting because electrons are much lighter, and therefore kinematically, this allows us to look for dark matter particles which are either in the mega electron volts or even directly in the electron volt range, if this dark matter particle, for example, is absorbed by an electron in a nucleus. So today, direct detection experiments have become a very diverse way of looking for new physics. And I will be trying to cover, at least briefly, some of the searches that are taking place today. So again, starting with the more conventional approach, which is nuclear recoils. Your experimental strategy is to look for a massive or as big as possible target. You put it underground to cover it from, for example, from any source of radiation. And you, of course, put a shielding around it to protect it from the radioactivity of the cave as well. Just as an example, this is a schematic view of the LZ experiment, which is a liquid xenon experiment, which is operating nowadays. The number of events from dark matter that you expect in this kind of experiments is simply the scattering cross-section, which is the probability of interacting of your dark matter with the nucleus, integrated to all the velocities that the dark matter can have in the halo, and to all the energies that your experiment can have. A crucial quantity here is the exposure, which essentially measures how rich and patient you are. This is how much material can you get and how long is your experiment going to run. In terms of the scattering cross-section, this is where all your particle physics input is. Okay, if you have chosen a particular dark matter model, this is going to determine how large or small your scattering cross-section with ordinary protons or neutrons is. But also, this is sensitive to the details of nuclear physics in terms of form factors for the different targets, and also, the different specifics of each detector. For example, if you're talking about solid-state physics, if you have a germanium or silicon target, for example. Okay, so it's beautiful as a field to study because it allows you to look into very different areas of physics. It is conventional, or let's say it was conventional until 10 years ago, more or less, to split this scattering cross-section into two components, which are, one of them is insensitive to the spin of either the dark matter or the nucleus, and the other one is what we call spin-dependent. These contributions originate at different levels in the microscopic description of the dark matter, and in principle, both of them are there. However, it is generally assumed that the spin-independent cross-section is larger, simply because it scales with the number of nucleons squared. It is said that it has a coherent contribution, sorry. Again, these also include nuclear form factors that encode the different coherent scattering with the nucleus. If nothing is found, as it has been the case in the past few decades, you put upper limits on each corresponding cross-section. So what I'm going to present now, just as a summary of what is the status of searches at the moment, are the different upper bounds on the spin-independent and spin-dependent cross-section coming from different experiments nowadays. All right? So I started by showing LZ. Okay, LZ is one of the three major liquid xenon or double-phase xenon experiments nowadays. Okay, these are, for example, not only LZ, but also xenon, enton, and Panda X. This target is ideal. Xenon is a very heavy target, 130 something. And if you remember what I just said, the coherent factor, which is 130 something squared, favors this over lighter targets. Xenon is also easily scalable. So liquid xenon experiments have become very big in the last few years. These are the latest results just this year from the LZ experiment, not having found any events which are compatible with dark matter detection. They have derived an upper bound on the spin-independent cross-section as a function of the WIMP mass. As you can see, these type of experiments are extremely sensitive for dark matter masses above 10 GeV. For lower masses, their experimental threshold is not enough to see particles, and that's where you see a reduced sensitivity. Just to also put it into a context, the typical range of energies, which these, for example, analysis from xenon or from LZ was concentrated, is recoil energies in a window between 5 kilo-electron volt all the way up to 55 or 60 kilo-electron volt. And I will talk later on what are the implications of opening up this window as well. And again, just for context, these are 4.2 ton year of exposure, which is quite large. As I said before, liquid xenon experiments have been improving a lot in the past few decades. And you see it very clearly in this plot, which is adapted from a slide that Piero Ulio presented in IDM this year earlier. We started with essentially hundreds of kilograms of exposure experiments, such as Xenon 10 and Zeppelin. And very quickly, this technology has allowed us to reach to these 3 experiments where we are today. These are ton scale detectors, Panda X, Xenon N-ton, and LZ, all of which are still taking data. And they have been able to exclude or to probe WIMP dark matter particles up to a cross-section of 10 to the minus 47 centimeters squared. This is for a mass of 50 GeV. Liquid xenon is very good, but there are also argon experiments which are coming in the next years. Okay, we've seen, for example, that the liquid argon technology is also catching up quite quickly. Dark side 50, deep 3600, and the planned dark side 20K, which is going to be 20 ton of liquid argon, are going to allow, as you see, to reach sensitivities comparable to those that we will have with xenon. It is very interesting, therefore, to consider, for example, the complementary properties between both targets. I've been talking so far about the spin-independent cross-section, but like I said, the scattering cross-section can have 2 components. For the spin-dependent one, what you're looking for is a target material that has an unpaired neutron or an unpaired proton, because then you have a large angular momentum. One of these experiments was PICO, which was the successor of Picasso and Coupe, and which, employing a target with fluorine, managed to reach, again, almost 1.5 tons of 1.5 tons day exposure, which is quite a lot. The sensitivity, again, not having found any WIMPs, they've put an upper bound on the spin-dependent proton cross-section that you see in this plot. Okay, they are dominating, especially for masses below 100 GeV. For spin-dependent neutron, again, xenon is ideal because xenon has 2 isotopes, which is xenon 129 and xenon 131, which have an unpaired neutron. And LZ being so big, it is leading the spin-dependent nucleon neutron bounds, as you can see in this plot. However, because there is an interaction, a possible interaction, a mixing between proton and neutron spin states, it turns out that LZ can also put upper bounds on the spin-dependent cross-section with protons, which is comparable to that of PICO. Just to put them on the same plot, the line that I showed earlier for PICO is this orange band that you can see here, and this black line corresponds to the latest results from LZ. So again, you can see that we're ruling out large areas of the parameter space, at least for WIMP dark matter, for masses above 10 GeV or so. We shouldn't forget, though, I'm going to be talking mostly about direct detection, but there are some indirect searches which are also sensitive to the spin-dependent cross-section. And this is through capturing of dark matter in the sun. There is the possibility that dark matter crosses the sun, scatters off some of the nuclei, in particular the protons that the sun has there, and therefore, we have an overdensity of dark matter inside the sun. If dark matter then subsequently annihilates into neutrinos, then it can also be looked for in neutrino detectors. And these are bounds that have been obtained by KM3net, which is a neutrino detector on the bottom of the Mediterranean Sea. As you can see, this experiment and also IceCube that are going to be probing also large areas of masses in the range of 100 to 1 TeV. again, reinforcing this idea of complementarity between different searches. What happens at lower masses? Okay, I've been talking so far about particles of dark matter above 10 GeV. But below 10 GeV, we have also a different range of experiments with different technologies in which the idea is to lower the experimental threshold. So instead of increasing so much the target size, what we've realized is that if we lower the energy window at which we start taking data, we can be sensitive to much lighter dark matter particles. And this is the strategy that the super CDMS, Edelweiss, and CREST experiments have been looking for. What you can see here are the two brand new detectors that we're going to be installing, or are already installed actually, in super CDMS at SNOLAB. These are germanium and silicon detectors, about this size, about 20 centimeter wide and about 10 centimeters thick. And these are disposed in four different towers, which essentially interleave germanium and silicon detectors. We're employing here two technologies, one in which we discriminate between nuclear recoils and electron recoils very, very well by looking at the different combination of ionization and phonon signals. The discrimination is essentially 1 part in 10 to the 5. And this allows us to do what it is almost a background-free search for nuclear recoils at large energies. However, the star in our new detector are the so-called high voltage detectors. High voltage, just to put it into a context, is 100 volts. It's not more than that. But these employ the fact that with this voltage difference, we managed to amplify the signal that can be due to very light dark matter particles. So instead of that signal being below threshold, we just push it above threshold. And this allows us to look for dark matter particles in the sub-GeV regime. This is the expectation of the sensitivity that we expect to reach at the end of the first run in SNOLAB, is the dark blue area. If we manage to improve our threshold, which can be, is probably likely if we understand our backgrounds a little bit better, then we might be able to extend this, as you can see, to even 0.1 GeV, 100 MeV. So this is something worth looking forward to. And finally, our cryostat is big enough to host up to 200 kilograms of material. So if we get extra funding, and if we manage to run with an extra amount of silicon or germanium, then we might even get to scattering cross sections of order 10 to the minus 44 centimeters square, down to masses which are 50 MeV or so. Okay, so this technology is actually quite useful. It's been, and I also mentioned it earlier, okay, so far I've only been talking about scattering of dark matter with nuclei. However, if you start looking at what happens with electrons are much lighter, and therefore they can be accelerated much more easily. Experiments have realized that the dark matter signal could be hidden in what before was only considered the background. If we analyze dark matter electron data and compare with the expected background, you can actually put limits on the dark matter electron cross-section, which are also becoming very, very competitive. In particular, notice that this allows us to reach masses of the order of the kilo-electron volt. And again, as I said before also, if you're considering absorption, even lower than that. In this plot, I'm just quoting very quickly the results from Xenon and Ton, again, just a few days ago, which was probing, again, dark matter masses of the order of the kilo-electron volt. Okay, here the difference is whether the particle that mediates the interaction between your dark matter and the ordinary matter is light or heavy, and then you get a different dependence on the momentum. So that's why you see different curves in this plot, which is for light mediators, and in this plot, which is for heavy ones. Why is this interesting? Okay, we are not just probing areas of the parameter space just because. There are some theoretical models that have been proposed for dark matter in the KeV range, in which dark matter is not produced by freeze out, is produced by what we call freezing, which is possible, for example, if there are particles in the bath in the early universe that either decay into our dark matter particles or annihilate into these candidates, okay? So to me, what's interesting is that if we find dark matter in this range of the parameter space, we would be actually accessing a different cosmological history of the universe than what we have been assuming for a long time. This is, again, just for complementarity. I'm showing the searches for dark photons or action-like particles, which are also could be absorbed onto an electron in our dark matter experiment, and then that electron would just be emitted. Again, the main signal would just be ionization, and for that reason also xenon enton and xenon-based experiments have also been quite useful here, okay? You can see here the bounds for dark photons or action-like particles. When looking for light dark matter, understanding the signal in your experiment is crucial. We are talking about looking for essentially potentially an excess, which is very close to the experimental threshold. And also in the last few years, it's been realized that there is a potential effect, which is not new physics, it's actually standard model physics, that could mean that we have sensitivity to lower masses than we ever thought. And this is the Migdal effect. The Migdal effect consists of the emission of an electron after the nuclear recoil of a neutral particle with a target nucleus. This is applicable to dark matter because dark matter is neutral, and it would mean that what we before considered to be only a nuclear recoil at low energies can be a simultaneous nuclear recoil and electron recoil. How is that important? Well, typically, the nuclear recoil is going to remain below threshold, as we can see here, for very light dark matter particles. This, as an example, is the spectrum for a germanium target with a mass of 0.5 GeV. However, the emitted electron would have a larger energy and is therefore much more easily observed. You can see here the spectrum for the emitted electron. Again, let me insist, this is not new physics. It was postulated in the 40s, and the only channels, however, is that we have not observed this yet at low energy. It does improve the sensitivity to low mass WIMPs, and actually, direct detection collaborations have been using the Migdal effect, or assuming that the Migdal effect is real, to derive better bounds at low masses. So you can see analysis by the DAMIC collaboration, LUX, Xenon, Super-CDMS, all of which assume a particular signal and then extend their bounds. Okay, this is the plot from DAMIC. We have a similar plot from Super-CDMS. However, again, we have not tested this. We have not seen the Migdal effect at low energy yet. So the real challenge is actually first to observe it, characterize it, and then understand if these lines that if these contours that we're plotting are correct or not. One of the experiments that have been looking for the Migdal effect is XENU, or well, actually using the XENU TPC at the Livermore National Laboratory. This is employing liquid xenon. I think it was 1 year ago. They've been looking for the Migdal effect, and they couldn't find it. What I'm showing here is the spectrum of this experiment. It's in 2023. The Migdal effect, it was expected to have approximately, was essentially 50 counts or so. However, the best fit for the experimental data showed that it was at least about 1 order of magnitude smaller. There was no evidence of the Migdal effect where it should have been. One has to be very cautious. This could have been due to the electron and the nucleus recombining in a different way in xenon, mostly because both tracks would be near. So it might be that we don't understand very well what is the response of liquid xenon to a simultaneous emission of a nuclear and electron recoil. So still more data is needed. An experiment that we're collaborating with is the Migdal collaboration. This is taking place at the Rutherford Appleton Laboratory, and again, the goal is to shoot a neutron and observe the simultaneous emission of a nuclear recoil and electron recoil in a gas of CF4. The first phase of experiment is already running, and the second phase is planned to start in 2025. So stay tuned, because again, this is important, not only to look for dark matter and to derive better bounds, but also if you ever find dark matter at a low mass, we need to know whether there is a Migdal effect or not that can lead to a misreconstruction of the mass, for example. Right, up to now, everything was very simple. We only had two contributions for the scattering cross-section, spin-independent, spin-dependent. But back in 2012, it was realized that actually this is a simplification. The most general Lagrangian that you can write at the non-relativistic level between dark matter and the nucleus contains at least 14 different operators, 14 for the proton and 14 for the neutron, if you assume, for example, some kind of isospin violation. Operator 1 is the standard spin-independent that I talked about already. Operator 4 is the standard spin-dependent operator that I already mentioned as well. Or the others, as you can see, can have non-trivial dependencies on either the velocity or the momentum. This again is very interesting because it might mean that the spectrum of dark matter that you assume to be an exponential decaying with the energy might be slightly different. For example, I'm comparing here the spectrum expected for an EFT momentum-dependent operator in blue, together with a canonical spectrum that you would expect from the spin-independent cross-section, for example. Notice here that if your experimental threshold is not low enough, you would miss part of this signal. And this actually looks like a canonical spectrum, for example. You might misreconstruct not only the mass of the dark matter particle, but the whole operator itself. So for this reason, it is very, very important to have low threshold experiments that help you disentangle what happens below at energies which are low enough. So not only this, but also if you observe an excess in a dark matter experiment like this, if your canonical signal is this kind of exponentials, you might misinterpret this as some sort of new background. So again, it is very important to have different signatures that you can incorporate in your experiment for all these different operators. And also for that reason, remember when I told you earlier, the window in energies that we're looking for, it can actually be extended. And precisely to study these momentum-dependent operators, it is actually advantageous to look for energy or recoils which exceed the 60 kiloelectron volts that I showed before. In an analysis that we did a couple of years ago, we showed that the ideal upper bound or upper energy in xenon would be about 500 keV, and in argon it could be even higher. The reason that that region of the parameter space is completely available to experiments, and you only have to look there. If you look at an extended energy window, for example, for operator 10, which is momentum dependent, this might allow you to improve the upper bound or the sensitivity curve by more than 1 order of magnitude without doing anything to the experiment. It's just looking for data at higher energies. Of course, this has been done then after we suggested that. The LSET collaboration in 2024 has released data, of course, upper bounds, because they haven't seen any signal compatible with dark matter. But they've employed an energy window which extends now to 300 kiloelectron volts. And look what this made possible. The operator 10, for example, again, a momentum-dependent operator, they have obtained upper bounds which extend up to, well, higher than 1 TeV. We also did an analysis in Super CDMS. This was in 2022, in which we also included the possibility of having isospin violation. So we were looking at each effective field theory operator, but considering that the coupling to protons could be different to the coupling to neutrons. So these two analyses are complementary, and also notice that our analysis, being in Super CDMS, extend to much lower masses. Right, so if we come back to the calculation of number of events that I showed you earlier. There we go again. One of the properties that I mentioned earlier was that we have to integrate to absolutely all the velocities that the dark matter halo, that the particles in the dark matter halo have. So this is actually sensitive to astrophysical parameters in the halo, not only the local dark matter density, but also the velocity distribution function, which is how are dark matter particles distributed in the halo. Most of what we know about the dark matter halo is done necessarily through numerical simulations. So what I'm showing here is the results from the Eagle high-resolution simulation, and these are some reconstructions of the velocity distribution that were calculated for Milky Way-like halos. What one does is to look for galaxies in the computer that look like the Milky Way, and then see, for example, whether this resembles a Maxwellian distribution function, okay? And it was seen by these researchers, Nassim Bothornia and collaborators in 2016, that indeed it was very, very similar to a thermal distribution, a Maxwellian distribution. More recently, we've also been able to employ data from the Gaia satellite. Gaia has been tracking the positions and velocity of 2,000 million stars in our galaxy, which are a lot of stars. It is very interesting to think that the velocities and positions of these stars could actually be related to the distribution of dark matter as well. This is, you can infer the dark matter velocity density through the velocity density of stars in our galaxy. And through doing that, we've realized, for example, that there are what we call non-virialized components. These are components which are not thermalized, and which imply a modification from this Maxwellian shape that I showed you earlier. A very prominent feature was the so-called, at the moment it was called the sausage, Gaia sausage, because people thought that this resembled a sausage, and I'm not really quite sure why, but anyways. And this implied a shift of dark matter particles in the high velocity range. And this is particularly interesting. If your dark matter particles are faster than you thought they were, you have more energy available in your experiment to look for them. So your experiment is more sensitive to low mass dark matter as well. Perhaps more interestingly, we've also observed coherent motion of stars in our galaxy. This is what we call streams. It's like stars are coherently following the same direction. And again, being a purely gravitational effect, you would expect that dark matter also follows that distribution. So a lot of work has been done in the last few years to identify all the possible streams in the Milky Way and trying to incorporate them also in the predictions for direct dark matter detection. It's also been realized, and again, I mean, notice that this depends a lot on the history or the merging history of our own Milky Way halo. Objects which were merged, which were captured later, they are still there, okay? And that's the case, for example, of the Large Magellanic Cloud. The Large Magellanic Cloud can induce again more particles in the high velocity window. And this, when you look at exclusion curves, this means that you actually have sensitivity to very, very low mass dark matter particles, okay? Notice here that we can go even to 700 kilometers per second, when the Maxwellian halo was only limiting you to about 600 or 500 kilometers per second. All of this, of course, as we have not discovered dark matter yet, only imply a change in the exclusion lines. But if we ever have a signal for dark matter, this is going to be crucial to be able to identify the mass of the dark matter properly. And of course, this has also been implemented by Bothornia and collaborators in EFT operators as well. Since we're talking about the dark matter halo, there is a final feature that I cannot resist mentioning again, okay? Probably the only signal, and let me put there quotation marks if you want, that we had for dark matter was coming from this Italian experiment, the Dama-Libra collaboration. Dama-Libra observed what seems like the annual modulation in scatterings from dark matter. I think they've already have data for 22 cycles, but I think I stopped this plot a couple of years ago. And as you can see here, the data are quite consistent with a sinusoidal behavior, which is what you expect from the velocity of the Earth inside the dark matter halo. What you're seeing here, the reason for the modulation is for half of the year, the Earth is following, or the Earth velocity is contributing to the sun's velocity inside the halo, and for half of the year, you're just going slower. So that means that you have a different population of dark matter particles impacting your experiment. The modulation effect is about the 7% of the whole signal. And again, the Dama-Libra signal was in principle compatible with that. However, And I think, as you probably all know, the interpretation in terms of dark matter is incompatible with the non-observation by any other observable that we've done. Any of the ones that I presented and some others that I will present in a minute. And therefore, well, it remains a challenge to explain what's going on in Gamma Libra, but also it opens up the need to test Gamma Libra with exactly the same target and exactly the same kind of experimental analysis. This is looking for annual modulation with sodium iodine. And this is something that several collaborations have taken up. Most notably, Anais and Cosine, but also Sabor, Cosinus, Dark Matter Eyes, etc. Again, spoiler alert, we have not seen any modulation. What I'm showing here is the 3-year results for Anais. The green line corresponds to the modulation observed by Gamma Libra, and the blue and red correspond to different analyses by the Anais collaboration. And you can see here already by eye, they are quite different. Anais doesn't see any modulation. These results are not published yet, but I got them from Maria Martinez, which is a member of the Anais collaboration, who presented them a couple of weeks ago in the multi-dark IBS meeting in Seoul, in Daejeon. You can see here the modulation, the red dots correspond to Gamma. As you can see here, the error for Gamma is very small. They've been running for, I think, 22 cycles already, for an energy window of 1 to 6 keV and 2 to 6 keV. The black dots correspond to the results of Anais, which are already 4.3 sigma away from Gamma. They're going to be able to exclude it at 5 sigma if nothing happens. I think it is by spring next year. And cosine is slightly higher, but still 3.5 or 3.6 sigma incompatible with Gamma. Okay, so as you can see here, when you look for the Gamma annual modulation, even with the same target, you just don't see it. Thank you. Right, so where are we at the moment? So the only thing that's clear is that since we don't have any dark matter signal, what we've done is excluding some areas of the parameter space. Here I'm putting all these results together only just for the spin-independent cross-section. LZ is just here, and just remember again, there are 2 avenues here. Either we increase the target size and we are able to explore lower values of the scattering cross-section, or we reduce the experimental energy threshold, and therefore we can look for lighter dark matter particles. You may be wondering, what is this blue area? This blue area is actually a complication that might arise in the coming few years. Actually, it's already important just now. This blue area represents where dark matter experiments are going to observe neutrinos, either from atmospheric sources or from the sun. And the difficulty with neutrinos is that they will look very much like dark matter. We refer to this as the neutrino floor or neutrino fog, just because it is an area of the parameter space where we cannot perform a background-free search anymore. And actually, our dark matter search is going to be limited to essentially to be very, very close to that neutrino floor. Neutrinos interact in dark matter experiments in 2 different ways. We can either interact coherently with the whole nucleus, and this is just a standard model process that have been recently observed in spallation source experiments. So we know it is there, okay? The coherent collaboration has observed this 3 times. In 2017 on, what was it, sorry? Cesium iodine, sorry, yeah. Liquid argon, and more recently also in germanium. But neutrinos can also interact with electrons in our detector. So we have both ways in which we are going to see neutrinos. Again, remember that this is just standard model physics so far. The coherent elastic neutrino scattering is mediated by the Z boson, neutral current, whereas the electron scattering, you can have contributions from neutral or charged current depending on the nature of your neutrino. Again, since it is only standard model that we're seeing, in principle, we only have 1 parameter, if you want, which is the sine squared theta W, which would be measured, if you want to say it in a positive way, at very, very low energies. However, and I think this is very interesting, if we have any source of new physics in the neutrinos, it might also show up as a new contribution to coherent neutrino scattering. Here I'm exemplifying this with a Z prime, just a new gauge boson that could be also responsible, for example, to contributions to any other low energy observable. Here we will have a new contribution from new physics to the coherent neutrino scattering that would also show up in our dark matter experiments. This implies also that the neutrino floor, where we've calculated it, might rise. It might be actually higher up. And this makes it possible also to observe a new low mass mediator. So it's actually quite interesting. Which neutrinos are we seeing? As you can see here, this is the number of neutrinos that we will see in our direct detection experiments, and the calculation is completely analogous to that of dark matter. First, we have the scattering cross-section of neutrinos with my target, which I already showed before. It's either the standard model cross-section or standard model plus new contributions. Next, we have to consider what is the flux of neutrinos that is coming to our experiment. This is the different contributions to the neutrino flux. At high energies, we have atmospheric neutrinos, which are very energetic, but not as abundant as solar neutrinos, which come below 20 MeV. Among solar neutrinos, the most energetic contributions come from boronate neutrinos, and the most abundant are PP neutrinos, but these ones are only below essentially half an MeV. So again, I mean, all these populations of neutrinos in principle might be accessible. Also, just to put it into a context, we also heard from some of the previous talks the diffuse supernova neutrino background. It is at a quite inconvenient area of the parameter space in which it is not as energetic as atmospheric neutrinos and not as abundant as solar neutrinos. So detecting is, as we've already heard, is a real challenge. The neutrinos that are produced in the sun, they are produced as electron neutrinos, but then through matter effects and the distance, they oscillate into the three different flavors. So something that is actually very interesting in the detection experiments is that we are going to be sensitive to the three populations of the three flavors of neutrinos, electron, muon, and tau neutrinos. And this is actually an advantage, and it gives us complementarity to dedicated neutrino experiments. These are the different probabilities of oscillation between electron neutrinos and tau neutrinos, for example. And you see that for boronate neutrinos, which are quite energetic, the probability of oscillation to tau neutrinos is actually about 30%. So we have a large portion of the flux in tau neutrinos. Again, this is how neutrinos are going to look like in my direct detection experiments as a function of the energy. Boronate neutrinos gives us the hope of detecting them recently, and it might actually have happened because we get recoil energies above 1 keV, which is where our sensitivity, for example, in LZ and XENO might lie. For the other families of neutrinos, the recoil energy has to be very low to observe them. And in particular, notice here CNR neutrinos are just where we have sensitivity in solid state detector, germanium and silicon, for example. Again, just for context, this is how dark matter would look like. So your 6 GeV WIMP is identical to boronate neutrinos, and a 100 GeV WIMP or higher is identical to atmospheric neutrinos. Right, so again, this might be a complication if you're looking for dark matter, but then why not looking for neutrinos with the same device? We don't have to change anything, it's just doing a different analysis. And so what we've been doing lately is realizing that because of their low energy threshold, an excellent energy resolution, because they're sensitive to both nuclear and electron recoils, and because we're going to be able to see the three neutrino flavors, direct detection experiments are actually a complementary test of new neutrino physics, complementary to dedicated neutrino experiments. There have actually been recent claims by Sinon and Ton and Panda X for Ton that they have data consistent with the observation of the first boronate neutrinos. Okay, so this is a reality. I mean, luckily, because neutrinos are there, but this is going to happen in the next few years. And something that we've been working on in the last few years is actually see how direct detection can actually set constraints on the so-called non-standard interaction, for example, for neutrinos, or different ultraviolet models for neutrino physics. Just as an example, I'm going to show you a particular case in which through electron recoils, which are in red, and nuclear recoils, which are in blue, we can cover up areas of the parameters of non-standard interactions. And here, for example, I've chosen a contribution to electron-neutrino scattering with either protons, neutrons, or electrons. The shaded areas, the dark areas, for example, here, these orange and blue, correspond to the limits from xenon and ton and LZ. These are real limits right now. The lines that you see here, the red line and the green line, correspond to the best fit values from oscillation experiments. So it tells you, for example, that anything above this line is excluded, and also below. In this parameterization, this term can be either positive or negative, okay? So, of course, you can see here that the detection experiments are not yet competitive with neutrino experiments, but the future correspond to actually these dotted lines. And you can see, for example, that for Darwin, which is going to be a multi-ton xenon experiment, we might reach the sensitivity able to improve by 1 order of magnitude the coupling to electrons, and about also 1 order of magnitude the coupling to protons. There are analyses exploring the whole parameter space, and you will see that in some operators, direct detection experiments are better than in others, okay? But our claim is that they are complementary. So again, I mean, just to summarize this last part, direct detection experiments, I think they are becoming crucial to constrain neutrino parameters, and actually they will need to be included in global neutrino parameter fits, which is what we're doing next. All right, let me finish here. I've been talking mostly about direct dark matter detection, so just the message to take home is we have not discovered dark matter yet, apparently. Liquid noble gases are excellent at high masses, but there is a plethora of very good ideas and very good experiments below 1 GeV. And in particular, looking for electron recoils is really, really cool. There are open questions about the dark matter distribution and the Migdal effect, which are relevant to properly reconstruct dark matter particles with low masses. And finally, this is our reality. Direct dark matter detections have become actually quite good neutrino detectors. Let me finish here, and thank you very much.
So you mentioned this Migdal effect that hasn't been observed. So, but I wonder if could be applied also for neutrinos. So, yes. And it has been observed also.
It would apply to neutrinos as well. And actually, where is it? I mean, here, everything is just coming from, notice that you need a neutral particle to just be able to impact the nucleus, okay? And the reason you're also emitting an electron is because you can consider this electronic cloud as being in a perturbed potential from the accelerated nucleus. So yes, it would also apply to neutrinos, yes.
And are there any dedicated search for this kind of effect?
So we only look for the Migdal effect, and then we assume that it is the same for dark matter and neutrinos, because again, it wouldn't depend on the nature of the particle that is incoming. It's only pertaining to the nucleus that is recoiling. But obviously, you don't look for the Migdal effect with neutrinos. We are looking for the Migdal effect with neutrons, just because it's easier. You can have neutrons. I mean, shooting neutrinos is going to be much more difficult. The cross section is much smaller. Okay, but yes, I mean the only thing with the Migdal effect is that you don't have to change anything in your experimental setup. If the Migdal effect is true, then the spectrum that you would expect instead of being this one is this one plus this one. And the same for neutrinos. So remember, for neutrinos, I was showing the spectrum without Migdal effect here. And then with Migdal effect, you would expect this plus this. What is the difference? For dark matter particles, we don't know what the dark matter mass is. And therefore, if the dark matter is very light, we don't see the main contribution. And we might only be accessing the Migdal contribution. Then it is important. For neutrinos, I mean, luckily we know that neutrinos are there. And we know where this is, okay? So Migdal actually doesn't give you that much for neutrinos because the Migdal contribution is about 4 orders of magnitude smaller than the main contribution. What you might have here, for example, is that the Migdal contribution from bottom 8 is going to make your search for the diffuse supernova neutrino background through coherent scattering much more complicated. But if you're not looking through coherent scattering, then it also doesn't matter.
Thank you. More questions? One of the students? Okay.
We've got a question there.
Why liquid xenon and now liquid argon?
Well, it's not the same collaborations, okay? Some people started working with liquid xenon, and then it's a different collaboration that is now employing liquid argon. I think it's I'm not an experimentalist, so I won't be able to give you 100%. But I mean, both targets are very interesting because they are self-shielding. That means that if you put a large volume of any of these liquid noble gases, you can actually use a shell around your fiducial volume that is going to absorb some part of the background. So you're left with an inside which is extremely clean. This happens for both xenon and argon. I think, if I'm not mistaken, but I'm not an experimentalist and someone might correct me here, okay, that argon has very nice scintillation properties, so probably that's also why they want to employ argon.
It's cheaper.
Oh, it's also cheaper, yeah, okay.
Much cheaper.
Yeah. Mm-hmm. So yeah, the difference something that is actually very interesting to look for dark matter is that they have very different masses. So xenon is very heavy. So that's also why this, for us, is very good because we are looking for a coherent factor. So that depends on A squared. But argon is very light, and that might give you another handle to discriminate between masses of dark matter. Argon will be more effective to look for dark matter masses in the range of 50 GeV or so.
If not, yes.
Okay, so our next speaker is Carlos Yaguna. It's a pleasure for me to. Okay, so our next speaker is Carlos Yaguna. It's a pleasure for me to present him. He's professor at the Universidad Pedagógica y Tecnológica de Colombia in Tunja. So today he's going to present a work that we done in collaboration a few years ago. So, Carlos.
What do you mean a few years ago? It's what just published.
Okay, sorry.
Okay, so yeah, indeed, I'm going to talk about a specific dark matter model in which the dark matter particle is a Dirac fermion. So to connect this with the previous talk, we were talking about wind dark matter in this case, okay? So the talk is based on this recent paper done in collaboration with Oscar Zapata. So I'm going to describe what the model is, what are its parameters, what is phenomenology, and how we could test it in the future. So first of all, we could ask, okay, why another dark matter model? Okay, aren't they enough? Well, it's certainly true that hundreds of dark matter models have been proposed in the literature. This is our recent plot that illustrates some of them. And I can guarantee you that not all of those that have been published are here. But the point is, why more dark matter models? Well, critically, one point is that we don't know which is the correct dark matter model, and certainly there are no restrictions on what nature has actually chosen. So there is no reason to believe that one of these is actually the correct one. And moreover, we have found, rather surprisingly, that some simple models actually have not been explored yet. And at this stage, simplicity is quite important. Why? Because we lack signals, okay? We don't have any experimental signals so far that allow us to discriminate among all these different candidates that would at least point to our preferred directions in this plane. So simplicity, when this is the case, simplicity is an important criterion. So we will be working with minimal models of dark matter. What does minimal model mean in this case? So the idea is we're going to extend the standard model. We certainly need to extend the standard model. So we are going to extend it, but just a little bit. It's not that we are going to double the spectrum just to explain the dark matter, but we are going to add just few new fields. And the idea is that some of these, or at least one of them, will be the dark matter particle. As a consequence, we will usually have a small number of free parameters. Okay? And this implies that the model tends to be quite predictive. You don't have the freedom to do whatever you want in these kind of scenarios because of this. In dark matter models, something else that we usually need is a stabilizing symmetry. Okay? So we know that the dark matter particle is stable. It was there in the early universe and still here around us today. So I cannot simply add new fields and hope that one of these will be stable and will be the dark matter, because this very rarely will happen. Typically, we have to impose by hand this stability. And the way to do that from a model building perspective is to impose a symmetry, an additional symmetry beyond the standard model gauge symmetry. Now, this symmetry is usually a C2. Okay, under a C2, you have two kinds of particles. Ones are odd under the symmetry, and ones are even. The evens are usually the standard model particles. The odds are the new particles, your dark sector if you want. And as a result, the lightest odd particle is necessarily stable, and consequently a dark matter candidate. Now, we've been exploring, however, over the past few years, alternative symmetries. So not C2, but using Cn, where n is larger than 2. Okay? And it turns out that these scenarios are quite rich from a phenomenological perspective. The main feature that we found was that you can easily realize multi-component dark matter within this framework. So normally it is assumed that the dark matter is explained by just one particle, but it doesn't have to be so. I mean, what we have measured is the total density of this dark matter, and in principle, there could be 2, 3, or more particles that contribute to this total density. So we have explored models with C3, C4, C5, C6, and C7. One example here is shown here graphically for a C7 symmetry with 3 fields. And this is the parameter space for the masses of the 3 fields. And we see that there are some regions where all 3 of them are stable, and therefore dark matter particles. They all contribute to the dark matter density. There are regions where you have 2 of them that are stable, or dark matter, and there are also regions where you only have 1. Okay? The other novelty that appears in this scenario is that you have new dark matter processes, because all these particles, for example, all these 3 are charged under the Cn symmetry. There will be processes that involve all of them, which you wouldn't have if they were not charged under the same symmetry. But as I said, so far we have been focused on multi-component scenarios. So one could ask whether this idea could also be useful for single component dark matter. What happens if we replace this usual C2 with a Cn where n is larger than 2? Specifically, the model I will present here is a model in which we have just one scalar and 2 chiral fermions. Okay? And the symmetry that we're going to use is a C6. Okay? So the idea is that under the standard model particles, they don't transform under the C6. And then we have a dark sector that consists of these 3 new particles, the scalar and the 2 chiral fermions. And these particles, these new particles, are standard model singlets. So they don't have any gauge interactions, but they have different transformation properties under the C6. Okay? And now there will be, because we have a scalar here, this scalar necessarily will interact with the Higgs, and this scalar will also interact with the other particles that are charge under the C6. And therefore, the Higgs serves as a connection, as a link between the dark sector and the standard model particles. Okay? So this is an explicit example of what is called Higgs portal models. Okay? So we have a dark sector and a standard model sector, and the Higgs provides the link between these two. Specifically, the new particles transform in this way under the C6. Okay? So the scalar field goes into this omega 6 to the cube, which means goes to minus itself. But the other two fields acquire a phase. Okay? The fermion, the left-handed fermion acquires a phase, and the right-handed fermion acquires a different phase. Okay? Which is shown here. And these are all the ingredients that we have in this new model. Okay? So I have specified all I need. Okay? I have said what is the symmetry, what are the new fields, and how these new fields transform under the full symmetry. Now we can write down the modular Lagrangian that is consistent with this extended symmetry and with this extended particle content. And what do we get? Well, let's see. First of all, we notice that there is a new interaction term between the three new fields that we have. Okay? And it's this one here. It's a Yukawa interaction between the scalar, the left-handed fermion, and the right-handed fermion. Okay? They all transform under the C6, and the charges are such that this term is invariant. Okay? And interestingly, this is the only interaction term that we can have for the fermion. And we cannot even write a mass term for the fermion because, as we said, the fermion is charged under the C6, so it is forbidden by the symmetry. From here, then, the idea is that the scalar will acquire a non-zero VEP, a vacuum expectation value, and if this, once it does so, this term will become a mass term, just as in the standard model. Okay? And this will be then a Dirac mass term for the fermion. Okay? And this fermion only appears in this term and will automatically be stable. Okay? So if it is stable, given that it is neutral, it is also a good dark matter candidate. And that will be our dark matter particle in this model. Okay? So it's the fermion that comes here, that, as I said, the left and right-handed component are both charged under the C6. What about the scalar? Where the new scalar potential is given by this expression. This is quite familiar because this is the usual singlet scalar potential, where we have a quadratic term, a quartic term, and we have an interaction with the Higgs. Okay, and that's it. We don't have anything else. Okay, so these three terms. And the novelty here is that now this field acquires a VEV. The Higgs doublet also acquires a VEV, and therefore here we will have a mixing between these two fields. Okay, so at the end, these two will mix, and we will have two mass eigenstates we will denote as S and H. Okay, so these are the mass eigenstates, and I have a new parameter in the scalar sector, which is the mixing angle between these two particles. And the good news is that this implies that there should be new collider signals associated with this field, because what this is telling us is that the Higgs that was observed at the LHC is not exactly a standard model. Okay? There is a small mixing due to the contribution with this additional scalar. And therefore, if I'm able to measure precisely the properties of this scalar that was observed at the LHC, I should be able to determine that there is a deviation due to the mix with this additional particle. So to summarize, this is what we have in the model at the end. So I have two new particles. One is the dark matter, which, as we said, is a dark matter, a Dirac fermion. And we also have a new scalar. Okay? That's all we have. Okay? The dark matter and a new scalar. And we only have 4 free parameters. So the two masses, the mass of the dark matter and the mass of the scalar, Then I have the mixing angle in the scalar sector, and this coupling, which is the Higgs-Portal coupling, the coupling between the scalar and the Higgs. Okay? So that's all. There is nothing else in this model. And the Lagrangian, we already saw it. So the question is whether this model is actually viable. Okay? Because when you have few parameters, the risk is that you cannot satisfy all the constraints. So let's look at the phenomenology of this scenario. Well, this is as I said, this is a wind model. So the dark matter particle is the fermion, and this is a weakly interacting massive particle. So the relic density is determined by dark matter annihilations, and some of the relevant processes are shown here. So remember that the fermion interacts only with this scalar, okay? And in this case, there are two scalar fields, at least in the mass eigenstate basis. And these are some of the processes that are possible in this case. So it can annihilate into scalars and Higgses in this way through an S channel and also through an T channel. Regarding direct detection, what we have is the usual diagram mediated by the two scalars. Okay? Again, we have both contributions should be taken into account. So here are some results that we got. So first of all, in this figure, we illustrate the dark matter relic density. And each line corresponds to a different mass of the scalar. This is the mass of the dark matter particle, the fermion, and for a given value of the other two couplings. What is relevant here is that we can see that there are dark matter constraints can be satisfied in different regions. Remember that the dark matter should be along this horizontal band. And there are three regions that are clearly distinguishable. First of all, we have the Higgs resonance, which is very common here, located at half the Higgs mass. Then we have the other resonance, which varies with mass, is the heavy resonance associated with this scalar. Okay, so we see that there are indeed points like here and here where we satisfy the relic density at that resonance. And finally, we also have regions at higher masses, like this point here. We see at higher masses, the relic density has this behavior which is induced by this process. So it is also possible to satisfy the relic density in that case. Okay? So these are the three regions that are relevant, or the three different regions where the dark matter constraint can be satisfied. Now, to check whether this is consistent with direct detection or not, we did a likelihood analysis of the parameter space. And the results we got are shown in this figure. So all the parameters of these models are here, because remember, we have only four, okay? The two masses, sine theta, and the couple. So what we see here, first of all, is that indeed, this model is viable. All these points are consistent with all known experimental bounds, okay, from cosmology and also from colliders. The three regions can be easily distinguished here in this plane. So this vertical line is simply the Higgs resonance. This other line is the heavy resonance. And this region here is the heavy mass region, what I call the heavy mass region, where the annihilation is into two scalars. So we see that the region is consistent, that the model is consistent, and also we see that the value of the mixing angle is different along these regions. So in these two regions, it tends to be rather large, but in these other regions, it's preferred to be small. Okay. This other figure shows instead the coupling, the Higgs-Portal coupling. Again, the three regions can be distinguished. This is one, this is other, and this is the other region. And we see that we can reach masses up to 60 eV or so, and down to 100 GeVs. Okay? So we have a wide range of masses where the model is consistent. And this by itself is non-trivial. Now, what are the predictions then for this model? Well, here we have a plot illustrating indirect detection and direct detection. So for indirect detection, we have the value of sigma v as a function of mass for different channels. Okay? The the annihilation into scalar is important in the early universe, but it is velocity suppressed. So we see here that it is down in this region. The most relevant channels are then TT bar, Ws, and C, as expected, but all of them are like below 10 to the minus 27 or so. So it's not very promising from indirect detection perspective. Very different is the situation with direct detection, which is illustrated here in this plot. So the different colors here indicate the different regions. So the green part is the Higgs resonance. The blue part is the heavy resonance, and the red part is the annihilation into the heavy mass region, what I call it. See? Okay, and we impose the limit, the current limit, and that's why there is a line here where there are no models above it, because we are imposing by default here. And we see that there is a large fraction of models that are consistent. This region here, or this line, is the sensitivity of future experiments. So we see that there is a significant fraction of models that are within the sensitivity of future experiments. So there is the possibility of observing a signal induced by the dark matter fermion predicted in this model. Now, recently, as David told us, there was a new new limit from the LC collaboration that improved this current bound by about 1 order of magnitude. So this implies, for instance, that this small region here is already excluded. Okay, so we see how there is this important interplay between recent data and dark matter model building. The other two regions, however, are still viable. To conclude, then, I have presented a minimal model, what I call the minimal model for singlet Dirac dark matter. So the model is based on a C6 symmetry. So we replace the usual C2 with a C6. Okay, that's the main novelty. And we wanted to have Dirac dark matter. Okay, the model is quite simple. It contains just 4 free parameters: the 2 masses, the mixing angle in the scalar sector, and the scalar portal, the Higgs portal coupling. Okay, that's all. So you don't have much freedom, and that means that the model is very predictive. And indeed, we saw that the parameter space and the different predictions for direct and indirect detection. So we found that it is indeed viable. There is a wide range of masses and parameters where we can satisfy all known bounds from collider and also from cosmology, and it is testable. Okay? So in particular, we saw that direct detection looks quite promising. And who knows, it may be that this is indeed the correct model for dark matter. Thanks.
So thanks, Carlos, for the talk. So questions? 1, 2, 3.
Hi, Professor, and thank you for your interesting talk. I just have a very simple question. Why did you choose those charges when you, those charge assignations?
Yes. Okay. So because we wanted to have a massive dark matter particle. Yeah, you cannot, you have to be sure, for instance, when you choose the charges, you have to be sure, for instance, that the fermion, that you don't have, let's say, a free particle. Okay, so you have to ensure that they are such that there are interactions among them. Okay. And in particular, we wanted to generate this term so that at the end you get a Dirac mass term.
And that's the only way that you can generate it?
Within a 6-6, yes.
Okay, thank you.
Mm-hmm.
Okay, thank you very much for the nice talk. I would like to see the slide when you choose the 4 parameters of the model.
This one.
No, in colors. At the end, when you...
the results. Okay, this one.
Yes. I was seeing theta.
Sin theta, yes.
The red points are not excluded. It's so big.
Well, it's not so much. I mean, we include the bounds here. So here is 0.1, and notice that one order of magnitude is from here to here. So from here to here is about 0.3, and that's about the current limit. So you see, one order of magnitude is this, so this is about factor 2 or 3. But this is consistent. I mean, you can check in the paper.
Okay, thank you.
Carlos, I was wondering about the chose set C symmetry. What do you think this is the minimal? Because in principle, you can build a chiral fermion mass with another simple charges, maybe set 4 or something like that. Or what happened?
For set 4, you can do it for Majorana fermion. Yeah, for a Dirac fermion, it doesn't work. So indeed, this is the minimal you get for a Dirac dark matter. Yes. It is not possible. I mean, you can play with the charges and see that it doesn't work.
Okay.
More questions? Wait.
What is going the slide of the DM fermion? What is the
What is like
dark matter fermion in
what-
the diagram fermion? Yes,
Yeah.
this. I don't understand what is the sequence of the events for production of dark matter in this. First production, this new scalar particle, and then the DM, or
Okay, so remember that this is a Wimmer scenario. So this particle, the fermion has interaction with the scalars and so on, and the scalar interact with the standard Boile field. So it will be thermal. So it will initially have a thermal abundance. So what you want to do then is reduce this thermal abundance through dark matter annihilations. Okay, so it is produced thermally.
Hi, Professor. Thank you for the talk. I have a question related with the model. I know the normal models, SU, for example, the SU3, SU2, etc., the SO, but to me it's not clear what is the definition of the symmetries, and what is the connection between the C symmetries and the 6 in the number.
Yes, so it has to do with the possible charges that you have. So you see, there is a C6, so this means that it's e to the 2 pi I over 6. So for example, you have C4, instead of a 6 here, you will get a C4. So these are rotations since it is a C6, rotation by multiples of 60 degrees. Okay, so this is a discrete symmetry. When you have a C2, you only have 1 minus 1. If you have a C4, you have 1 I minus 1 minus I. Okay, and C6, then you.
Thank you so much.
follow.
The very last question.
So thank you very much for giving me the opportunity to talk about this. Let me first apologize for the people that come from Sila 5 because this talk is rather similar to that I did there. The idea here is to combine neutrino masses and neutrino models. First of all, I will start motivating a little bit the dark matter that have a lot of gravitational evidence. And from this one, there is one a scenario of very generic way to explain dark matter that is through a particle. This is the same diagram that Carlos already showed us. And there is a lot of possibilities for the dark matter as a particle. And in particular, if we impose that the dark matter is a WIMP, that is a rather canonical scenario, the minimal possibility is the singlet scalar, but the singlet scalar is already excluded for indirect detection in most of the range of the parameters. So the next to simplest model is the, sorry for the small letter here, the inner doublet. So the idea here is just to extend the standard model with another scalar doublet, but that doesn't develop a vacuum expectation value. So this is a second doublet in the standard model. These two particles are neutral, the real part of the new inner Higgs and the imaginary part. And the small of them can be a good dark matter candidate because of the doublet nature of this particle. This particle can have interaction with the gauge boson, and this opens one important window that is called the Larmage window between around 500 GeV and several TePs. This when the parameter space of this model is explored, for example here, or in this paper by Carlos and Farinaldo, there is all these possibilities that are compatible with direct detection, but can be proved with indirect detection. For example, Hex is already taking data and reaching this parameter space. And in the future, we will have CTA that possibly will explore the full parameter space and can either discover or exclude this kind of models. So in the context of neutrino physics, this model is very important because automatically appears in the hidden sector where the neutrino masses can be analyzed. For example, in general, we can have massive neutrino masses in the standard model, either as Majorana or Dirac. In Majorana, it is possible because we automatically have this non-renormalizable operator called the Weinberg operator after this paper that violate lepton number by 2 units. And with the realization of this operator, we can have small neutrino masses, usually because these associated scales suppress sufficiently the associated complex in the specific model. In the case of Dirac, in principle, we can have automatically neutrino masses if we introduce right-handed neutrinos. However, the resulting conflict could be rather small. So in order to have one explanation of the lightness of neutrinos, we need to forbid this kind of renormalizable operator. And this Dirac operator can be, for example, forbidden if you impose that the lepton number is a good symmetry. At this level, then, the violation of lepton number is not allowed, and this automatically, and this made that this term automatically disappears. And in addition, in order to avoid the generation of the Majorana mass, we need to impose one additional, for example, SEP2 symmetry to have, again, massless neutrinos at this level, and we only need to realize this operator on some a scale like this one. So after that, we need to explore how can generate these operators with a specific mechanism. For example, how to generate these operators at one loop order. So this study have been done systematically. And for example, here was done in the context only of neutrino masses. And when Carlos and Oscar some time ago, we imposed in addition that the models also include the possibility of a dark matter candidate. So in addition to the neutrino masses at one loop, we impose by hand a Z2 symmetry. There are 4 topologies available for that. and restricting the SU2 multiplets to be singlet, double, or triplets, we end up with 45 possibilities, and most of them are already studied. The same way in the Dirac case, we can realize this renormalizable operator by adding a new hidden sector with particles that are automatically stable and for, again, an scotogenic scenario. In this realization, for example, we have, in addition to the inner doublet that appears also here, additional particles. I will focus in that way in this simple topology of the so-called radiative seesaw model in either the Majorana or Dirac case. For example, for Majorana, the model is quite straightforward. In addition to right-handed neutrinos and the inner doublet that at odd under the Z2, we have these realizations in which the particle inside the loop belongs to the dark sector, and the standard model is even under the Z2 symmetry. For the Dirac case, this simple topology requires a little bit more work because we need, in addition to the Z2, another symmetry in general to guarantee not only the stability, but the absence of the Majorana mass for the right-handed neutrinos. And the most natural way here to get the masses is with a Dirac heavy mediator, while in the Majorana case, we have a Majorana mediator. But in general, we can have all the possibilities. We can have Majorana neutrino masses with Dirac mediator by complicating the inner scalar sector, or we can have, as shown in this paper, Dirac neutrino masses with a Majorana mediator. Note that in the case of Dirac, we have, in addition at least, one extra singlet scalar in the inner sector. So in order to have more appealing model for Dirac neutrino masses, it is good try to reduce the two required symmetries to only one. For example, one B-L symmetry. This one done simultaneously in these two works. And this is, for example, the realization when we have now, again, one normalizable operator to the dimension phi, in which we include, in addition, a new singlet scalar that develops a BEP. When this particle breaks spontaneously this symmetry, it automatically appear the Dirac neutrino mass. Here, for example, this Dirac fermion is just vector-like, and there is one charge, B-L charge arbitrary, that I call here the charge R, that circulate the loop. And there are many possible realizations. So the symmetry can be just reduced to one, and the good thing here is that if the symmetry is local, for example, it is no longer necessary to impose the Z2 by hand, but is just a consequence of a new local symmetry that is compatible with the gauge principle. So now, with this one B-L is one active symmetry. Now I will check what happens when this extra symmetry is secluded in the sense that affects only the particles in the hidden sector. There, we need to include a set of elementary fermions that are charged under the new gauge symmetry. The minimal number to have a compatible model is at least 5 chiral fermions, And these charges need to satisfy at least the cubic and linear anomalies that imply these two equations. In order to find out the solution to these two equations, there are several methods that are inspired, for example, in what happened in the standard model. In the standard model, we have, for example, the first generation with 15 chiral fermions. We can normalize the hypercharge to one integer value. So these fermions correspond to the three doublets in two colors, red, blue, and green, the three-quart singlet, up singlet, the three down singlets, and the lepton doublet, and the right-handed electron. So if we add these charges, they add to 0, and the cubics sum also add to 0. So the set of hypercharge in the standard model automatically satisfy, obviously, these anomaly conditions. So what happens if we choose, for example, one scalar of charge 3? So we compare this integer with this, representing the doublet and the up quark, and this 1 minus 4 gives 3, can couple to the Higgs, and acquires a mass through the vacuum expectation value of the Higgs, like Carlos showed before. And the same happens for the three masses for the down and the mass for the electron. However, there is 1 minus 3 left aside that implies that one of the 15 chiral fermion is still massless. So, in general, we need to solve these two equations. One method, for example, is to use the fact that the SU3 cross SU2 symmetry includes one abelian component. So if we choose one arbitrary one family model with combination of the diagonal elements of the Gell-Mann and the SU2 matrices, it is easy to form a set of 12 fermion particles that automatically satisfy the anomaly condition. So we need only to randomly vary here the parameters A, B, and C, and automatically all these solutions start to appear. There is a method that can be used to find some of the solutions that is very easy to implement numerically. In general, then, we end up with a set of chiral fermions in which we will have a dark Higgs mechanism, in which the chiral fermions can couple to the dark Higgs and acquire masses. In general, this mechanism will be enough to give masses to all the fermions. Some of them are massless and are denoted here by these chi letters, while the massive one is denoted with the psi. Because in general there is a lot of massive fermions, then we will have multi-component dark matter. The multi-component appear because this symmetry is local. In the case of Carlos, in the case of the Z6 was imposed by hand, so it is possible only have one Dirac fermion, but here in general we have a lot. Because also of the local symmetry, we have a dark photon Z prime that is good respect to the binomial size symmetry, because this had a lot less restriction and more freedom to explore. And because of the dark Higgs that acquire vacuum expectation vacuum expectation value, in general we have two mediators for the dark matter phenomenology. So in this kind of models, in general, we have several dark sectors that communicate with the standard model through either the set prime or the inner Higgs scalar that mix into two mass eigenstates that I will denote here at S and H. In these two mediator models, as I mentioned before, we have two neutral states that have a mixing, and the photon and the set mix through the so-called kinetic mixing. With this mixing, the kinetic mixing, the set prime can mix with either the set of the photon, and for example, when the dark matter particles are annihilating into them through the kinetic mixing, they can connect with the standard model particles. Usually, we can choose the set prime to be sufficiently, the mass of the set prime to be sufficiently small, and we can have this kind of diagrams that can be used to enhance the parameter space. And because we have several dark matter candidates, dark matter independent components, we can have conversion between them. And we also have contribution from the singlet, from the dark Higgs, like in the model of Carlos. So one specific example is to build Dirac neutrino masses in which the massless states are chosen to be the right-handed neutrinos. We can then realize this non-renormalizable Dirac operator. And one specific example is, for example, with this solution with 6 integers. There are 2 repeated integers that can be associated to right-handed neutrinos and 2 pairs of integers that can be associated to Dirac fermion dark matter candidates. So we have ended up with this massive Lagrangian for one of the Dirac fermion and the other one, and the two of them are dark matter candidate, and here the Riemann symmetry is Z5. 2 minutes. So in general, we can use this kind of models to explain scotogenic realization of these scenarios. For the idea here is to simplify them to have the simpler possible inner scalar sector. Here, for example, we need to guarantee that there is an order degeneracy in the charges of this mediator in order to have masses for all the neutrinos with the simple inner sectors. So here, for example, we have 2 Majorana fermions, and here we have 2 Dirac fermions. In these realizations, the Majorana case, for example, have been recently studied by this paper by Babu and collaborators. With this scenario, when we have 2 Majorana fermions, 3 Dirac massive fermions. Here, there is no massless fermions at all. All of them are massive, and they can have several dark matter candidates simultaneously. And in the case of the Dirac, we can have, for example, this model with 3 right-handed neutrinos and 3 massive Dirac fermions. This is a work in progress that Andres will be presented later in more detail. So in conclusion, in this scotogenic model, we can explain dark matter and neutrino masses and mixing. We can have diverse realization with many prediction because we have multi-component dark matter with several messengers.
Okay, so you mentioned that you have thousands of these models. So I was wondering if you have made some statistics regarding, for example, what is more likely if you have to have one dark matter particle, two dark matter particles, three, or so on, or it doesn't make sense to study this.
So, for example, in this case, suppose that the secluded dark sector have all these components, all of this one. So here the only difference is just the specific complexity of the dark sector, and because this is completely unknown, in principle, these 1,000 of possibilities have the same, how to say, statistical probability. It's just what happened in the nature if it realized through this kind of dark matter.
Thank you, Diego, for very nice talk. My question is why you only consider two anomaly triangle anomalies?
Because it's secluded. So this particle, the standard model are completely neutral. So the only anomaly condition for this kind of model is just this. Yes, because there is all of them are singlets under the standard model. The only gauge group is an abelian group, so the only anomaly equation are those.
Thank you, Diego, for this nice talk. I have a question about the vacuum stability of the Higgs potential in those models with a new doublet scalar. Is it possible to spoil the stability of the Higgs potential by the inclusion of this new Higgs doublet, or what kind of conditions can you impose over the couplings to ensure vacuum stability?
Yes, in fact, in this kind of inner doublet models here, yes, if you doesn't include anything else, the stability is quite good. So the only parameters are the parameters in the scalar potential that are quite stable under, for example, the RG evolution. But in the scotogenic scenario, there appears some Yukawa with fermions that have one strong dependence with the GAT scale. So we, in general, can only guarantee that this doublet is bezeless, doesn't acquire until certain scale. Maybe after that scale, the potential is no longer stable. So in principle, you need to figure out what to do for this point. For example, choose the parameters another way to keep the stability to larger scale. Just ignore that and assume that there is one ultraviolet completion that solve that problem. So in general, yes, you have stability issues in this kind of scenarios.